Basics of Outage Management System in Electricity Distribution. Hello and welcome from Down Under Grid Tech. In this video you will learn the basic principles of how Distribution Network Service Providers Outage Management System works. Distribution Network Service Providers, DNSPs, maintain reliable power supply for customers. They continually upgrade network equipment, ensuring a robust command and control system. This system includes outage notifications and alarms within the Network Operations Control Center. Therefore, staying updated with the latest trends and technology is crucial, especially for communicating with customers during faults and emergencies, such as bushfires, storms, cyclones, or everyday operational issues. Today, regulatory authorities establish service-level agreements and key performance indicators to hold DNSPs accountable during outages. Response time is a critical aspect of this accountability. DNSPs actively communicate with customers during an outage, providing estimated restoration times. They use various channels like SMS, emails, outage tracker websites, and interactive voice recordings for customers who call to report outages or seek the latest updates. This comprehensive approach enhances the overall customer service experience. In outage management systems, two primary types of outages exist: planned and unplanned outages. Planned outages are typically scheduled for the replacement of aging electrical network equipment, which necessitates the isolation of a specific portion of the electrical network. As a result, these outages are well-informed, pre-arranged operations managed within the Network Control Center. In addition to meticulous planning, this process involves notifying impacted customers well in advance. These planned outages undergo thorough simulation and testing within the Network Planning Division. This meticulous approach is crucial, especially when dealing with life support customers or other sensitive entities such as hospitals and critical infrastructure like transportation systems, including traffic lights and street lights. This ensures minimal disruption and a smooth transition during planned maintenance activities. Within the outage management system, these planned maintenance outages exemplify DNSP's proactive approach, an instance where prevention is indeed better than a cure. The Network Strategy and Reliability Team maintains a continuous assessment of network performance, ensuring alignment with the dynamic fluctuations in demand and supply. This diligent evaluation prompts necessary actions to enhance reliability and meet the evolving needs of customers. Another critical aspect of outages involves fault, emergency, or unplanned outages. These incidents can stem from various causes, such as a car colliding with a utility pole or a tree branch falling onto electrical wires. In such scenarios, protective electrical network devices play a crucial role. They swiftly come into action, preventing further disaster by isolating the faulty section of the network. This rapid response not only safeguards the electrical infrastructure but also ensures the safety of the people and properties connected to the affected network. A typical electricity distribution network is divided into two main segments: the high voltage and the low voltage network. The Network Operations Control Centers responsible for monitoring and maintaining the network, as well as making sure safe and uninterrupted electricity supply to the customers. However, they only have visibility and control over a specific portion of the high voltage network. This control is made possible through supervisory control and data acquisition (SCADA) systems, where network devices continuously report of their current status, operational parameters, and overall health. Therefore, from this last SCADA high-voltage network control point to the downstream customer's electricity meter, distribution network service providers rely on the Internet of Things infrastructure, primarily if customers have advanced metering infrastructure, such as smart meters. It's worth noting that for customers with traditional manual electricity meters, DNSPs depend on customers reporting outages through phone calls. In today's video, we'll delve into a fundamental fault in the distribution electrical network that leads to an unplanned outage. We'll explore the various methods employed by distribution network service providers to detect these faulty network segments, pinpoint the specific malfunctioning network devices, and effectively communicate with impacted customers throughout the fault mitigation process and the entire unplanned outage lifecycle, right up to the restoration of service. In our first example, we'll illustrate a fault occurring at a distribution transformer substation. This fault involves the dropout fuse, also known as the high voltage fuse, blowing due to an overcurrent fault within the network. As depicted, a pole-mounted distribution transformer substation serves multiple entities, which includes 3 households, a shopping center, and a school. In the event of a fault within the network, the dropout fuse, a critical protection device situated before the transformer, plays a pivotal role. When a fault occurs, this fuse is designed to blow, thereby preventing potential damage to the expensive transformer. This proactive measure not only safeguards the transformer but also prevents the risk of it exploding and creating electrical sparks that could lead to fires, making the neighborhood significantly safer. In this scenario, the dropout fuse, being a non-telemetered network protection device, has blown, resulting in an unplanned outage. The distribution network service provider remains unaware of this outage due to the lack of visibility into this specific power disruption. This lack of awareness is exacerbated by the absence of advanced metering infrastructure, smart meters. As a result, DNSP relies on customers to report power outages. In response to the outage, customers from Household 1, the school administration, and the shopping center management have decided to contact the DNSP. At this juncture, the DNSP's outage management system call center begins receiving calls from these customers, all reporting the power outage. At this point, when call center representatives receive customer calls reporting the power outage, their first step is to register these calls by identifying and locating the customers within the DNSP's outage management system. To do this effectively, the outage management system integrates information from various sources. Number 1. Customer Information System, CIS. The system maintains and provides customer details, such as their address, telephone number, meter number, and any critical or hazard-related information associated with individual customers. This information feeds the outage management system, which helps identify and reaching out to affected customers efficiently. Number 2. Metering and transformer relationship. The outage management system maintains information about which customer meters are supplied by which distribution transformer. This relationship mapping is crucial in pinpointing the potential area of the outage. 3. Geographic Information System, GIS. The DNSP's GIS database stores geographic coordinates for every network component, including transformers, substations, poles, and lines. This GIS data allows the DNSP to map the physical location of assets, enabling them to identify the affected area on the network. By integrating these data sources, the DNSP can swiftly identify the location of the reported outage, and correlate it with the relevant faulty network components and impacted customers. This comprehensive approach aids in quickly assessing the extent of the outage and formulating a response plan to restore power efficiently. In this advanced outage management scenario, the system runs a prediction algorithm based on customer calls received, that is, which customer meters are being served by which transformer. This customer meter and transformer relationship helps predict a potential outage at a faulty distribution transformer substation. Since the DNSP has precise geographic coordinates for this distribution substation, they can promptly dispatch a field crew to this specific faulty location to address the issue and restore power. In second scenario, the distribution network service provider has modernized the grid by integrating advanced metering infrastructure, AMI, which exemplifies the application of the Internet of Things, IoT. Now, when a dropout fuse triggers an outage, the AMI-enabled smart meters send immediate, last-gasp signals. These signals are logged by the DNSP's outage management system, OMS. The OMS then analyzes the network hierarchy, mapping which meters are connected to which distribution transformers. It aggregates the last-gasp signals from individual meters to identify a single event per transformer. This method equips the DNSP with real-time insights into the scale and specifics of the outage, eliminating the need to rely on customer calls. Consequently, the DNSP can proactively initiate broadcasting outage information to customers and expedite the restoration process without delay. In the third and final example, consider a scenario where a remote-controlled recloser makes several unsuccessful attempts to re-engage and eventually locks out, resulting in a high-voltage network outage. As a SCADA, supervisory control and data acquisition, component, the recloser triggers an alarm and logs an incident in the DNSP's outage management system. This immediate notification alerts the network operations control center about the event as it unfolds. Outages originating from such SCADA events are addressed and rectified through a process known as FLISA, fault location, isolation, and service restoration. This self-healing mechanism is a hallmark of many advanced distribution management systems, enabling them to swiftly respond to and remediate interruptions in power delivery.